Hello everyone, and welcome to reInvent 2020. You are here because you want to learn how organizations leverage Amazon Web Services to detect extreme weather events. My name is Yudhijit. Aerospace and satellite companies count on me to help them architect systems to securely communicate with satellites, develop machine learning frameworks, and act quickly and reliably on the business intelligence gathered from the space. Paul Grambauer, a cloud data scientist from Fireball International, will join us to explain how his company saves lives and property by partnering with AWS to detect and mitigate extreme weather events. In today's presentation, let's start by discussing the increased frequency of natural disasters. Next, you'll be interested to learn about two key Amazon Web Services that can help humanity react to these disasters: Ground Station and the machine learning stack. You are technical folks, so you'll definitely enjoy a sample architecture diagram that enables people to ingest, process, and disseminate satellite data. You'll definitely appreciate the live demo for ideas to bring to your application, and you'll feel inspired by a few quick stories of how companies are using Amazon Web Services today, and will love the deep dive into Fireball's architectures and products. Hurricanes and wildfires, floods and droughts. Every day brings news of an extreme weather event causing havoc in some or the other part of the world. The last few decades have seen an increased frequency of natural disasters, which have resulted in substantial losses to life and property. The severe impact and complexity of such events highlights the critical need for disaster prevention and preparedness. One of the first lines of defense against natural disasters are data collection and prediction systems, which are reliable and resilient. What can we do to be prepared? We will explore two such systems in our session today. If you have a satellite and need a way to get its data back to Earth, consider AWS Ground Station as a way to turn your capital spend to operational spend. Don't build a ground station. Let us do it for you. Companies like yourself are fully self-servicing their contact scheduling in one of our 7 ground stations: Oregon, Ohio, Dublin, Stockholm, Bahrain, Cape Town, and Sydney. The satellite owners are able to achieve unthinkably low latencies to access their data, as the antennas are co-located at AWS's data centers. As a result, you are bringing the data from space to the cloud in real time. Companies around the world also value the fact that the reliability in satellite communication has increased many folds thanks to AWS Ground Station, and that is coming as a first-hand experience. As you will see in our demo, today when I take a satellite pass, I don't have my fingers crossed. As a matter of fact, everything is automated, and so you can communicate with your spacecraft without any human intervention, thus minimizing chances of human error and having the confidence that you won't ever miss your critical data. Many companies don't have expert machine learning practitioners on staff, and they value the fact that AWS has developed solutions in all the 3 layers of machine learning stack that allow everyday developers and data scientists to create and tune their models. Companies also value the fact that they can add solution-oriented intelligence to their applications through something as simple as an API call on top of developing and training their own models in SageMaker. But hold on, this is a space discussion. Where does machine learning come into the picture? Well, what we are seeing is more and more space companies embrace machine learning to process satellite imagery data. These services are empowering our customers to deliver results and take decisions at incredible speeds, something that's critically important when it comes to weather events. Are you curious as to what such an architecture would look like? Let me show you. This is an architecture that brings your data from the space through the antenna into the cloud through machine learning stack and gets deployed at the front end. Going left to right, we start from a satellite crossing an AWS antenna. AWS Ground Station takes care of scheduling and antenna control. It also gives you the choice to accept the data in a demodulated, decoded, error-corrected format, or in a digitized RF over IP format where you get to bring your own modem or software-defined radio. The EC2 instance then receives and processes the data and then stores it in S3 bucket. An important point to note here is that the entire infrastructure was set up at once using CloudFormation templates. The dumping of the data in the S3 bucket triggers an event to invoke a real-time inference Lambda function, which you see on the rightmost column. This Lambda function can call the SageMaker endpoints to do inferences on satellite imagery data and store the results in a database like DynamoDB. With Amplify, what you can do is you can connect end-user applications to your backend with just a few lines of code and then deploy them at scale. Now, in the middle column, what you see is SageMaker making it easy to build machine learning models and getting them ready for training by providing everything you need to quickly connect to your training data and to select and optimize the best algorithm and framework for your application. SageMaker includes hosted Jupyter notebooks that make it easy to explore and visualize your training data stored in S3. SageMaker Ground Truth is a fully managed data labeling service that lets you build highly accurate training data sets. In order to retrain your models in SageMaker, you can create a workflow that will use the image dumps from the same S3 bucket to continuously improve the training data and iterate on the models. Now, moving on to the part I am most excited about, a demo. Here is the image that I'll be showing in our demo, which I captured from NASA's Aqua satellite over the western coast of the United States. Aqua is a part of NASA's Earth observing system, orbiting the Earth at a height of 438 miles. We start the demo from AWS console. I will go into the ground station service where I will book a satellite contact with Aqua. And going to reserve contacts now, it will pop up the ground station console, showing all the ground stations I'm whitelisted for, the NORAD ID of the satellite, and all the AOS and LOS times of the upcoming passes. And I choose the one that over 64 degrees is a good elevation. I go to reserve contacts, and that's it. That's all I have to do to reserve a contact, and everything from here on is automated. Going to the EC2 dashboard, I have one instance running, which is the receiver instance to get the data and do L1 processing, and second instance that runs the IPOP software to do L2 processing. And then I'm looking at Kratos' data defender to see when the data comes, and I'm monitoring the satellite. Data is coming, so the satellite must be in the horizon of our Oregon antenna. Yes, it is. Looking at a public satellite tracking website, the satellite has entered the United States, and Data Defender is bringing the data reliably and consistently to me. It's a 12-minute pass. I'm passively monitoring it, and I will be tracking the satellite when it's over Canada. So now the signal should be falling at any time now. And the signal is falling. The instances will process the data, shut down automatically, and upload the data to S3, which we'll be seeing right here. And as we can see, the data is already in the S3. I'm going to the level 2 folder and downloading the image that I previously showed over there. And the image is getting downloaded. And this is the picture of the satellite over the western coast of the United States. If you look here closely, there are a few orange dots that the satellite marked. Those were the fires that were burning on the western coast, on the western side, when the pass was taken in early October. The next thing I'll be showing is the SageMaker part, where we are hosting a hurricane speed detection algorithm. Now, SageMaker allows you to host Jupyter notebooks, which is your Python development environment. Here we are using PyTorch framework, and the model has been trained for 2 hours, and it is ready to be deployed. So I'll be opening the notebook. And you can either deploy the model as a SageMaker endpoint, or you can run it locally. So the first portion of code I'll be highlighting is to deploy the model as a SageMaker endpoint. You can choose the type and size of the instance as shown here, also the number of instances. But before deploying it as a SageMaker endpoint, you might want to run it locally to test if your algorithm is behaving fine. So this is how you would do it. And using This particular code, you will pass a test image and see the result from it. So I'm going into the details of the SageMaker endpoint, copying the name here, going back to the SageMaker console, opening up the details of all my endpoints. I have one here, and if I click on it, it will show me the metrics of all the instances associated with that endpoint. If you scroll down, you'll be able to look at the metrics. And you can also look into the algorithms that you have running on the instance. Scrolling down and clicking on the one algorithm that I have here, you can have multiple algorithms hosted at your endpoint, but this is the one I have. And after that, as a test, I'll be passing one image that I got from NASA's MODIS website, and the image of a hurricane. This is the image of the hurricane that I'll be passing through the algorithm to test it locally. So passing it now, here's the name of the image, and running the inference, and we should get the hurricane speed as 115 knots, which is consistent with our expectation. So this was one image that we passed and you're seeing the result, but you can also do multiple images as batch jobs to parallelly process them. And as you can see, there's metadata from the inferences of passing all those images through the algorithm. Now going back to the ground station folder, which got an image, I have a real-time inference lambda running here, which has an S3 trigger. So whenever there is an object dumped in the S3, this will get triggered. And what it will do is going inside the lambda function. This is calling the SageMaker endpoint. The SageMaker endpoint is right here, embedded as an environment variable endpoint name. And it runs the inference and stores the result in a database of your choice. And what we have chosen here is DynamoDB. Now, the picture that came in from the ground station when we did the demo, me and Pavan Kumar Sundar from AWS R&D and Innovation, my colleague, when we did the demo, we did not have any hurricane over Oregon, thankfully. But if we did, this is how you would ingest, process, and store your results. Speaking of ingesting and storing satellite data, the Aerospace Corporation is leading the way to document how easy it is to collect and store data from Earth observation spacecrafts like JPSS. They're obtaining direct broadcast imagery from 3 of the sensors on board, namely ATMS, CRIS, and VIIRS, as seen in Section A. They are leveraging the worldwide distribution of AWS ground stations, seen here on Section B. In Section C, they describe how the process is sequenced end to end in an automated manner. The vehicle contact is scheduled as per their choice of spacecraft, ground station, and time. Just before the contact, the receiver instance gets launched, which then receives the data from the RF side directly into their VPC and archives it into S3 buckets. The processing instance then gets triggered to start and execute data processing steps like stripping the VIDA49 headers and L1 and L2 processing with RTSTPS and CSPP respectively. Finally, the process data is archived for storage. We are seeing more widespread adoption of AWS ground station based on the Aerospace Corporation's positive results. Moving on to the second half of our session. We all know about the devastation wildfires have been causing around the world in recent times. We see the news, and time and again we wonder if these incidents could have been detected and stopped earlier, or if the first responders could have been notified earlier. Well, guess what? The good people at Fireball International wondered too, and have come up with a solution to detect fire incidents and send alarms to authorities within minutes. To tell you all about it and more, it is my great pleasure to welcome Paul Grambauer as my guest today. Paul, the stage is yours.
Thanks, Udajit. As we've all seen in the media recently, wildfires, bushfires, brush fires, or whatever they're called in your part of the world, are increasing. And I'm very excited to be here today to share with you our experiences in large-scale analytic pipelines for wildfire detections. Wildfires are increasing in severity, duration, and impact on local communities, and in some cases, country economies. In early 2020, the Australian government announced a $2 billion bushfire relief package. Recent fires have devastated parts of California and Australia, as seen here during the 2019 and 2020 fire seasons. Wildfires that cause this level of impact are significant events that require the consolidated efforts of firefighting agencies on the ground and in the air. But these fires have all one thing in common. They start as a small, easily controllable fire, if you're able to allocate resources to the right location at the right time. Low latency in fire detection and alerting to first responders is paramount. As you can see in this example, it only takes 16 minutes for a large wildfire to form. Performance and scalability at every stage, acquisition, detection, and notification, allows Fireball to send alerts within 2 minutes of smoke detection. Early detection of fires allow emergency agencies to control a smaller fire with fewer resources, reducing the impact on surrounding communities and potentially loss of life. Fireball International is a global company. It's been formed using decades of experience in academic model of fire patterns and behaviours. We've taken this knowledge and, with the help of AWS, formed it into a highly efficient fire detection pipeline to rapidly alert first responders to potential incidents. Hello, my name is Paul Granbauer, and I form part of the Fireball team as a cloud data scientist. My role at Fireball is to interface the machine learning, the application development, and the data flow pipelines with AWS services to form a globally scalable early wildfire detection capability. Today, I'll provide you with a deep dive on how to obtain value from AWS services. I'll also share some of my personal top tips to streamline your implementations, so keep an eye out for those. As you would have noticed in this presentation title, Fireball uses multiple sensors from the ground, air, and space to feed the Fuego intelligence analytics platform, resulting in alerts via email, SMS, and web visualizations. From ground-based sensors, we currently acquire images of more than 500 cameras alone in the California area, resulting in 2.5 million images being scanned for fires per day. Satellite data is processed and stored in our S3 bucket within 5 minutes of acquisition, which allows us to augment and validate our ground-based sensor network. Minimization of latency between the data acquisition from the source sensors and our analytics pipeline is critical to deliver near real-time detection. By aggregating areas of detection across the ground and space network of sensors, we're able to more accurately predict the fire location and increase the levels of confidence before we send fire alerts. Just so you know, the following architecture diagrams are at a high level. Supporting these services are well-designed VPCs, security groups, and scalable infrastructure. From a technical perspective, all RDS Aurora clusters are configured as multi-AZ, with CPU-based scaling of instances. Scaling of our EKS node groups is controlled via Kubernetes, depending on the amount of data flowing through our analytics pipeline. This allows Fireball to rapidly grow the sensor network and user base without redesign of the intelligence platform. The platform architecture you see here was not what we started with. Rather, it was an evolutionary process. We evaluated designs via proof of concept, including those you normally see in web apps such as AWS Lambda API Gateway and DynamoDB. Then we eventually moved to containers. For the most part, our services are running hard 24/7, detecting fires globally. We needed to find a compromise between the simplicity of the serverless event-driven architectures versus traditional EC2 instance deployments. Container-based platforms allowed us to use our in-house Python skill sets, specific scientific modules, and the AWS SDKs, with the assurance that once the container is built, it would run as expected without any other dependencies. It was important for us to focus on delivering business value, and for these reasons, we selected AWS EKS as the container orchestration platform. I believe you need to keep control of your core business solutions, and what I mean by that is what differentiates you from others. To rapidly grow your business, services that support your core business like databases, network, persistent storage, and managed services may be better provided by AWS. EKS, RDS, and SQS were selected because they provide a solid foundation for us to build our services. Our data flow contains all the interesting stuff. As much as possible, we wanted to ingest into S3 as our raw data store. This includes ground sensors such as cameras and satellite analytics products. Technically, we've implemented an event-driven message pipeline using SQS with producers and consumers as scalable services on Kubernetes EKS. From an operational perspective, it was important for us to maintain visibility of message content on the queues. For this reason, we use JSON formatted messages rather than size-optimized formats such as protobuf. For EKS, we use managed node groups of various instance types for operational, data flow, and ML inference services. This allowed us to better tune our resources and optimize our costs. All of our services are stateless, and all data is retained in Aurora RDS for highly transactional content, S3 for image objects, and EFS for apps that required shared configuration. Which leads me to my first top tip. With regards to container-based services, it's quite a simple process to deploy container images into EKS. It's rather tricky to tune the performance of each of these services. Each service you deploy will have different resource requirements, depending on how it was developed. We found it essential to capture Kubernetes pod level metrics and to understand the Kubernetes scheduler rules. So these rules define the placement of pods or processes onto instances, and also which ones should be terminated when resource limits are exceeded. Our performance times range between 1 to 5 minutes for a detection until we performed this analysis and tuned our services. We found pods exceeding memory and CPU limits, resulting in premature pod terminations, and nobody wants that. Now we consistently detect and notify within 30 seconds of acquiring sensor data, using fewer EC2 instances. It is not uncommon to have specialist skills within a company that require access to specific AWS resources. For this reason, we've separated the detection pipeline and machine learning accounts. It also allows us to decouple our modules and to evolve into a truly fault-tolerant and highly available system. From a DevOps perspective, across all AWS accounts, we follow a standard CI/CD flow that you may be familiar with, being Git for source code control, AWS code build for building container images, code pipeline for CloudFormation deployments, and AWS ECR for container image registrations. Once registered in ECR, these container images are then deployed to EKS via customized configurations, which we store in Git. We use the same CI/CD process for microservices, web apps, API, and ML inference services. To assist with the ML training stage, we prepare a quality set of selected data appropriate for smoke detection from our detection platform. Once new information is obtained, our annotation team labels specific features for ingestion into the ML pipeline. Following successful ML training, the model is then pushed to our Git repo, which triggers a CI/CD pipeline to deploy into the detection platform. This completes the ML training cycle, allowing our data scientists to focus on optimization and training of the ML models. Now on to my next top tip. Everyone has secrets, but you know what? Don't tell the world. Instead, use AWS Secrets Manager to store database credentials and third-party API keys. This integrates really easily into Kubernetes secrets. There's a custom container that polls the AWS Secrets Manager, registers the secrets as Kubernetes secrets. This can now be directly used in your standard Kubernetes deployment configurations. Of course, you would be correct in thinking that there's a lot of fundamental AWS services that we use to help Fireball deliver its capabilities. For example, we use Code Pipeline to deploy our CloudFormation templates and Cognito for user management and authentication. We use CloudFormation to build all of our infrastructure requirements, from VPCs, EKS clusters, to S3 buckets and event triggers. These services allow us to handle unpredictable data spikes in a timely and cost-effective manner. Which leads me to my final top tip today. When it comes to transaction data at scale, it is important to check your AWS API calls. Resulting from rapid growth in the number of objects stored in S3, we identified cases where the cost for the AWS S3 sync calls were becoming significant. This is because the initial S3 list objects API call occurs before the upload process. It was easily mitigated by simply using an AWS S3 copy command instead. Other gotchas we encountered were too many EKS processes or pods polling SQS queues. You need to scale your services to be performant while not over allocating resources. Remember, API calls that return empty receives from an SQS queue is still classed as an API operation. So my recommendation here is to regularly inspect your AWS Cost Explorer to identify unexpected cost growth. So Fireball has an exciting future, which we all look forward to. We'll be pushing to new areas, such as deployment of camera networks with onboard ML inference for fire detection. With our growth, we're constantly looking for opportunities to improve our processes. We'll be reaching towards AWS SageMaker and ground station services even more to obtain a robust end-to-end ML lifecycle and timely acquisition of satellite data. We are very excited that in 2022, we'll be launching a new satellite specifically for fire detection. This will augment our existing network of sensors and also provide the capability to detect fires in areas previously void of suitable fire detection sensors. And with that, I would like to thank you for your time, and I hope you gained some value from my presentation today. Back to you, Udajit.
Wow, that was amazing. Paul, what you and your company do is not just brilliant in technology, but is also a source of inspiration for humanity. AWS is honored to be a part in your journey. To those who are listening, please check out the website fireball.international to learn more about this wonderful company. And if you want to learn more about Ground Station, read this excellent blog written by one of our solution architects, Nicholas Ansel, on how to downlink data from Earth observation satellites, just like how I did today. And when you're ready to talk to us, please visit AWS for Aerospace and Satellite Solutions website, and we can take it from there. Please do keep in mind that you don't have to take these steps all by yourself. We have reference architectures, playbooks, customer success stories, and dedicated solution architects like Nick, Pawan, and myself to design and implement your solutions with you. And that brings us to the end of our session. Hope you have enjoyed it and are excited about using AWS in your current and upcoming space missions. Please feel free to reach out to us over LinkedIn. And as always, we are happy to help and guide you in your journey to the stars through the cloud. Thank you.